here is V initial, and here is V final. And remember, we're bringing V final down to the tail of V initial. As the final point gets closer and closer to the initial point, the final velocity rotates closer and closer to the initial velocity. So what's happening with the vectors tail to tail, this vector is rotating up this way. And delta V is then the vector that connects the two tips. So in other words, this vector up here, which looks that way here, it looks like this here, it looks like that at the top. Notice that as the vectors get closer and closer, the difference between them becomes horizontal. Delta V takes on a horizontal direction. In other words, when we look at a very, very small time interval, delta V turns into a horizontal vector. In other words, for this initial point, it points where? Where does it point? It points towards the center of the circle. What that tells us is that the direction of the acceleration is toward the center. Toward the center of the circle. It doesn't matter what initial point we had chosen. We could have chosen an initial point up here, and then delta V would have pointed that way. We could have chosen an initial point over here, and delta V would have pointed that way. Down here, delta V would have pointed that way. It doesn't matter where the initial point is. Delta V, for a small time interval, will always point toward the center of the circle. We call that acceleration a centripetal acceleration. Centripetal means pointing toward the center. It is a central pointing acceleration. Very, very interesting. That is the direction of the acceleration. What is the magnitude of the acceleration? Let's figure that out next. I've redrawn our initial and final point again with their corresponding velocities. The initial velocity over here, final velocity up here. What we now want to do is to find the magnitude of the acceleration, so we don't need to worry about the vector nature of this acceleration anymore. We'll just look at the magnitudes here. The magnitudes of those vectors. In that case, we can also look at just the magnitudes here. We don't have to worry about the initial velocity. That still has the same magnitude as the final velocity. There. And likewise, we're looking at delta V, and I've redrawn this vector subtraction triangle over here. Again, we're going to ignore the directions here and just look at the magnitudes. Let's think about the motion from the initial point to the final point. As we rotate from the initial velocity point to the final velocity point, let's imagine that we rotate through an angle of theta. So from our initial point to our final point, let's imagine that that is an angle of theta, that the object has gone through an angle of theta in the circle. Well, what has happened to the velocity vector? I think you can see that because the velocity is always perpendicular to the radial line, if we rotate the radial line an angle theta, the velocity also rotates an angle theta. So the difference between this direction and that direction is also an angle of theta. You can go through the trigonometry in triangles here if you want. I'll leave that to you. What I'm just going to say is then that if we rotate an angle theta from the initial to the final point, that the velocity also rotates the same angle theta from the initial velocity to the final velocity. Let's look at this little triangle here. I'm going to make a triangle by connecting the initial to the final point. How long is that edge of the triangle? We know that this side is the radius of the circle r. This side is also the radius of the circle r. How long is this side? That's a little bit of a hard question, but we do know that the length of the arc, the length of the circle that connects those, is the distance that the object has traveled as it moves around the circle. Let's imagine that the time between the initial and the final point we'll call delta t. So delta t is the time interval from the initial to the final point. That's how much time it took for the object to rotate from the initial to the final point. This arc length is then the distance that the object travels. But it's traveling at a speed v for a time delta t, so that distance is v delta t. Remember, we've got to take the time interval to go to 0. As the time interval gets smaller and smaller, as these two lines get closer and closer together, notice that the physical distance between those 2 points gets closer and closer to that arc length between them. In other words, as the points get closer and closer, a straight line approximation between them is almost the same as the arc length. In other words, the arc length looks like closer and closer to a straight line. So we'll actually approximate the distance between them with this quantity v delta t, because we know we're going to have to take that time interval to go to 0 anyways. We're going to have to take those points to get closer and closer. Well, very good. What do we have? We've got 2 triangles here. One triangle that is a triangle with 2 equal sides. What's that? That's an isosceles triangle with an angle of theta between them. While over here we also have an isosceles triangle with 2 equal sides, v and v, and an angle of theta between them. Well, what does that mean? Those 2 triangles are similar to each other. They are both isosceles with the same angle between the equal sides. Those are similar triangles. What can we do? Well, we can say that the ratio of the lengths of the sides have to be the same. In other words, the length of the short side, which is v delta t, to the length of the side that's equal for this triangle must be the same as the length of the short side here, which is delta v, over the length of the side that is equal, which is v. Very, very good. We've got these proportions between these 2 triangles that we know have to be equal. Let's multiply both sides by v and divide by delta t. We've got delta v divided by delta t. Delta v over delta t is equal to, multiplying by v, we have v squared over r. But delta v over delta t, that is exactly what gives us the magnitude of the average acceleration. Letting delta t go to 0, we get the instantaneous acceleration. But delta v over delta t is equal to v squared over r. For a small time interval, there we go, that is our result. V squared over r. Let me just write that down. The instantaneous acceleration, in other words, the acceleration for a small time interval, for an object going around in a circle, the magnitude is v squared over r. And we know that acceleration points towards the center of the circle, so that is a centripetal acceleration. I'll write that with a little subscript c for centripetal. Let's back up and think about what we've just done here. I will tell you, you do not need to know that derivation. You do not need to be able to reproduce that derivation. I do want you to understand it, but the 2 things I want you to get from that are the direction of the acceleration for an object undergoing uniform circular motion points towards the center of the circle. It is a centripetal acceleration. The magnitude of that acceleration is v squared over r. The speed of the object squared divided by the radius of the circle. An object undergoing uniform circular motion, in other words, an object moving around a circle at a speed v with a radius of the circle r, is accelerating. The direction of that acceleration is towards the center of the circle, and the magnitude of that acceleration is v squared over r. Very, very good. Let's take a look at some physical examples of this. Here's my mass going around a circle again. It's undergoing uniform circular motion, which means it must be accelerating. The direction of the acceleration at any point in the motion is towards the center of the circle. Wherever it is, the acceleration is always towards the center. Well, if it is accelerating, there must be a force acting on it. What is that force? Well, the force, if there are no other forces acting on the object, the force must be equal to the mass, times the acceleration. And if the acceleration is directed towards the center, the force must be directed towards the center. So we must have a centripetal force. And what is that? M times the acceleration is mv squared over r. In order for an object to be undergoing uniform circular motion, there must be a force acting on it towards the center of the circle. Well, what force is acting on this little ball, keeping it moving in a circle? Well, it's the string, the tension in the string. So the string is constantly pulling on the ball. But what direction is that force? Well, we know the direction of the force from a tension is always along the direction of the string. But where does the string point? The string always points towards my hand in the center of the circle. If that string were to suddenly break or to suddenly stop exerting tension, what would happen? The object flies off and we do not have uniform circular motion anymore. It's that string that keeps the object moving in the circle. Very good. Let's stick some numbers in here. Let's imagine a car is going around a curve. The car had been coming along on a straight road, and then it goes into a curve to the left, and then there's another straight section up here. During the time that it is actually going through the curve, so in our picture maybe something like from here to here, during the time that it's actually going through the curve, it is undergoing essentially uniform circular motion. Well, if it's doing that, there must be a force acting on it toward the center of the circle. Where's the center of the circle? Well, if the curve looks like this, the center might be over here somewhere. There must be a force acting on the car toward the center in that direction. Where is that force coming from? What force is acting on the car? Think about it for a second. Then let me ask you another question. If this car were driving on a very, very icy road, what might happen? Well, it might slide off the road. Why would it do that? Think about what's the force acting on the car that keeps it on the road. It's friction. It is the friction between the tires and the road that creates that sideways force towards the center of the circle that keeps it on the road. If there were no friction, imagine the car is coming along and suddenly it hit a very, very icy patch, what would happen? It would just go straight. There would be no sideways force holding it into the curve, so to speak. It would just slide right off and go off the road. So it's friction acting on the car. What kind of friction? It's actually a different kind of friction than what we've talked about. It's a kind of friction called rolling friction, a sideways rolling friction, but we can think of it very similar to static frictional force. So we'll actually use our results from static friction and apply it in this case. Let's look at that car from behind. Let's imagine we're looking at it directly from behind, and let's draw a free body diagram.